X is equal to external, the F input, the external force. So this is if there was a mass connected, that's the one. This is if there was a frictional component, this one, and the spring constant Kx, if there was something there. Okay, so and in this particular case, if you say that there is no damping, then you come up with the exact same equation under undamped system. Undamped system means one is kinetic energy and one is potential energy, and they're permanent oscillator basically. So it's with the natural frequency, this particular one. And if you see this one, there is some magnitude and perpetual sinusoidal waveform. This angle is just the phase shift. It has no effect on the actual system behavior, like it is sinusoidal versus not. So it's harmonic oscillator. Identical to this one is an LC circuit, inductor and capacitive circuit. And exactly the same situation. First we had L Q dot double dot plus R Q dot plus 1 over C Q. And if there is an external voltage, we put V in. If there is not, okay. I have recording from the other session which I will put in. Periodically, you have to tell me if you are unable to hear, so I can adjust it. So acknowledge that one, please. Okay. So in this particular case, again, there is no resistive component. So if there is no resistive component, then this is identical to what the mechanical system was. Okay. And in the absence of an external voltage, this is a second order differential equation with simple harmonic movement, okay, with the natural frequency. So it is basically Q double dot plus 1 over LC Q is equal to 0. And this is if you notice this one, like Y double dot plus Y is equal to, or KY is equal to 0 when we do this one. If you talk about Laplace, we saw that when f square plus omega square is equal to 0, and that one directly do this one, and this omega square is, so omega is equal to natural frequency. Okay. I mean, this is a part of the differential equation course, but in this particular case, when we talk about omega square, and over here, this is essentially, okay, we should put omega square. So this is omega square is equal to 1 over LC, and omega is equal to 1 over LC square root. This is called the natural frequency, or oscillation frequency, basically. That's what it is. Okay. Now, we are actually going to talk about the system. So there are 2 or 3 key concepts. Number one, this is a mechanical system, physical mechanical system. And first thing we have to do is that the model, the systemic of the schematic of the model is like this one. So in this particular case, if the spring is present, you do this one. If the damper is present, you put this one. If the mass is present, you do this one. And this one is if there is an external force. So we need to know that how are we able to represent it like that one. Now, the first thing we have to do is we need to specify a node, and usually there is a point is given to us. In this particular case, there is only one node. Okay. And when it is one node over here, then we have to know how many forces are acting upon that node and in what direction. So at equilibrium point, there is an external force right here. Okay. When there is an external force right here, this was like, I remember in this particular case, like in the voltage case, there is external voltage. In this one, if there is an external, if there is none, then we do this one. So if there is an external force, we do this one. Okay. So that is an external force. And in some cases it's like this one, some cases is the other way. The direction is usually given. Okay. In this particular case is this one. So with this particular, so this we call a node. Okay. And we say that this is one of them. In this particular case, they say, okay, this is going this direction. And this node is represented by X. Now, under equilibrium position, there are three forces which are keeping it on the other side. Number one, Kx, Bv, Ma. So these are the three forces. Okay, when we do this one, so we can write it f of x. This is f external, not f of x, f external force with respect to time. Okay. So this is equal to Kx plus B. V is a velocity plus M acceleration. I'm going to write it again. Ax V x dot M x double dot. X dot is dx over dt. X double dot is d2x over dt2. So this is the model. Okay. I'm going to jump to the actual problem so you will see what is the behavior look like. So before we do that one, I want you to visualize some of the equations. Number one, when we talk about the analogy between the electrical and mechanical, the one is called the KVL, the other one is called KCL. Okay, so KVL is the voltage. So in the electrical system, in the mechanical system, you saw this particular node. Okay, and if we equated that one to a some sort of like a loop, this is called the mechanical analog or analogy number 2, and it is called the force voltage. The other one was, if you remember this particular case, okay, so this particular case, okay, and if you notice this one, the external force, and in the mechanical system, this is the external force, and the opposing forces are, remember this is a specific node, this point. The forces are, so if it is a f of t, and the other forces are, so in this node, the one force is M A, and the other one was B velocity. So this one would put MA plus BV. Okay, so these are the two forces, and I'm going to rewrite the exact same scenario over here. Okay, so this one. So if you talk about the voltage equation, so Vn is equal to Vr plus Vc. With this particular KVL analogy of the mechanical system, you will say F external force is equal to Fm plus Fb. That's what it is. If on the other hand you would use like that, like a node equation, so you can put like this was a loop with a current. Node is like you have a VA, then you can represent V1 Vn minus Va over R, or I would put that equation like this one. If this is a VA, Va minus Vn over R is equal to Va VA, that would be the loop equation, di over dt. So it is the current. The current through this one would be, so this is the analogy when we put this one. In our book, we are following the electrical system, this one, and the mechanical system, this one. So we will stick to this specific rule. So if there is a voltage, that correspond to mechanical force. If there is a current, that correspond to velocity. And do not forget, velocity is dx by dt. The current is equal to dq by dt. So fundamental element in the mechanical system is a displacement or a distance. The fundamental system, the value in electrical system is the charge. The current depends on that one. Resistance is identically equal to the friction. Capacitance is inversely directly proportional to 1 over k, or inversely proportional to the spring constant. Inductance L is equivalent. So it's like you can see. Similarly, the transformer, when you change like a voltage going up and down, the lever where the power or forces correspond to the lever length, basically. That's what it is. So now these are like 4 kind of system with this electrical and mechanical analogy, with the analogy like 2, as I said. So the mechanical system, this is translational, this is rotational. So in this translational, we put force, electrical, voltage. It's a repetition of the previous page. Velocity, the current, the displacement, the charge. These are, remember, this particular one is a fundamental element. In rotational, you will see angle theta. In the hydraulic, you will see the volume. Linear momentum, P is equal to mv, and the current is equal to n phi, or so it's basically phi is equal to essentially this is Li. Okay, so if we were to do this one again, damper directly replaced by a resistor, spring constant directly replaced by a capacitor, mass replaced by an inductor. Now these 3 are extremely important because we are talking about the force voltage analogy. So force, which is a time derivative of the power, okay, it is, there are 3 ways to represent. F is equal to ma, F is also equal to bv, ma is m x double dot, it is b x dot, it is also equal to kx. So 3 ways to represent the force, identical to this one. Okay, so if you look at this particular one, the voltage V is equal to L I dot okay, the first derivative, but it is ideally equal to L Q double dot. Okay, the time which do not forget, I is equal to dq over dt. This is the fundamental relationship between the charge and the current. Same is the case, L is equal, the voltage is also equal to Ri, which is R Q dot. It is also equal to 1 over C Q. Okay, so this is essentially some value which multiply by Q. And this was a VC was equal to actually 1 over, it was 1 over C I dt. That was a VC. Okay, so essentially all of those ones, this one, and this one, and they are equal to these 3. Now, this is important. The next one, these pages I got are one parameter to another one. So we're starting from this particular one, the displacement. we take the derivative of that one. So if we say dx by dt is equal to velocity. Remember, we are going from here to here, so we take the integral. Okay. Direct multiplication, the force is equal to kx. If there was a spring constant, equal to 1 over c, the capacitance. Let's not put that one. Let's not put it because I have another one. Similarly, the force is P is equal to mv, but at the same time, the force is equal to bv. This is velocity. Okay, and this one. So if you want to see the relationship, so there are F is equal to ma. Okay, and if you talk about this one, this is a m. Okay, and when we talk about the, how do I get to F is equal to ma? F is equal to kx, F is equal to bv, and F is equal to, if we go over here, the F is equal to, where do I go about that one? Let me see. F is equal to m. Okay, so this one, oh yeah, okay. So from here, if you take first derivative, okay, and then you take, this is the first derivative over here, and this is simple multiplication, and this one, so it is first derivative over here and the second derivative right here, and this is a multiplication of that one. So F, so if you can put that like F is equal to ma also. Okay, identical to this one in the electrical system. This E is electromotive force, which is actually the voltage. So voltage is equal to, the V is equal to 1 over C Q, one of them. V is equal to Ri, and the other one, the V is equal to, the voltage is equal to, just 1 second, 1 second. Can you guys hear me?
Yes, we can hear you.
Okay. So this is and the other one is basically voltage is equal to, again going from, remember this is a integral. When I go in this particular one, so this is a dq by dt, and if you go, this is simple multiplication, and there is another derivative over here. So it is, this one is V is equal to L Q double dot. So the relationship is basically these two pictures, this one and the other one, they are essentially directly related. So one parameter, how do you connect to the other one? Okay. So now let's talk about the actual system. This is essentially the same one, like one-to-one correspondence. You can replace with one element. Force you can replace with the voltage, and I usually use this word V. Velocity, the reason the book didn't use, because they use velocity for V, and then they use E, electromotive force. Okay, and you can replace with this one. Let's talk about the actual problem so we can see where the how we can represent this one. So this is a first order system. When we talk about the first order system, you can see that this is the external force. Okay, so one of them. So let's talk about, so this one, Vn is equal to Vr plus Vc. Is everybody with me so far? Because if you are not, I will stop and reevaluate. So acknowledge one way or the other, doesn't matter.
I get it.
Yes, sir.
Sounds good.
Yeah, we can hear you.
So far.
All right. So I want to make sure that we are on the same page, and my message is getting across for physically reasons, the internet option. Okay, so this is one of them. Let's talk about the mechanical system. The mechanical system, the external force. So F external is equal to, again, there are two forces and this is a node. And the two forces, if this is going this way, this is going this way. Okay, so one is FB plus FX. So far, so good, right?
Yes.
Yeah.
Yes.
I'm gonna keep calling out you guys. Okay, so I see that you are with me. Okay, now this one, our VR is equal to IR, and VC is what? One over C Q. Is that good? Okay. I, on the other hand, the current is I is equal to dq by dt. So this one would be or Q dot plus 1 over C Q. Let's divide it throughout by R. So 1 over R Vn is equal to Q dot plus 1 over RC Q. If there was no external force, this would be equal to 0. External voltage. Same is the case over here. Let's talk about this one. So FB is, I need help. What is FB equal to? In terms of like those displacements we talk about. The force exerted by the friction. So what do I represent? What are the values that I represent it with?
Velocity and B.
Okay, so B, V. What about FX, FK, FX? It's not FX, is actually what it should be. The force
FK?
to K. So what is that one going to be equal to?
KX.
Kx. Excellent. And velocity is B x dot plus Kx, and this is equal to external force, correct? Let's divide by B throughout. So x dot plus K over B x is equal to 1 over B F. So far, so good?
Professor, I have a question. What happens
Yes.
to the inertial force, which is MA?
Oh, this is not that is not available over here. It is only a spring damper
Oh, okay. So there's no mass.
because we didn't put it. I am only dealing with the first order system.
Okay, thank you.
You can either put a spring damper or you can put a like a mass damper. Mass damper. Okay. So the first order, when you put mass and spring together, that becomes a second order system. Now, if you put this one, what about this one? I ask you this particular question.
Conductor.
That is a first order system too. This is inductance, this is resistance. And that would be mass damper. Okay. So bottom line is you get this first order differential equation. First order differential equation. That's what you get. Okay. Now we talk about a big system, which is a second order system. Somebody was asking, who was asking that question, please?
I was asking about it, Anthony.
Anthony. Now we talk about this one. Remember the objective is that you will see that the electrical and mechanical system mathematical models, they are identical. Okay, under like you can have like a one way to represent, so you can convert from a mechanical system to electrical and vice versa. So this is a problem 435, where we are actually going to see that we can make the objective is to convert it to an electrical system. So as I said, that typically there are nodes which are given. So there are 3 nodes given over here. Okay. So the number one thing is to identify those nodes correctly. Okay. Sometimes they are not marked. If they are not marked, we have to be able to find them. Okay. Number 2, for each node, we need to have a free body diagram. Free body diagram. Okay. So let's draw that one. So free body diagram. Okay. It is, what is a free body diagram in electrical system equivalent? With that specifically node. So I will explain it. Remember this question. I am asking a free body diagram, first of all, for the mechanical system. So the free body diagram says that on each node, we write the equation of that one. So identify on node X1. By the way, they put V1, V2, they are X1, X2, the same thing basically in the nodes are. So at X1, this is a free body diagram. What is the external force? Okay. How many forces are on the other end, please? At equilibrium, there are 2 forces. One is called F, the damper is B1. And the F, K1. Okay, so this is a free body diagram for node number 1. So I can write it. F ext is equal to F B1 plus F K1. So far, so good?
Yes.
Okay. Now, second node right here. Let's do that one. So this was node number 1. Node number 2. Okay. So let's talk about this one. So I'm going to redraw this node. How many forces are connected on this side? 2 forces. Okay. So this is a F B1, F K1. Now this is tricky. What are the forces on the other end? I'll give you the 2 forces. Tell me which ones are those.
FM.
Uh-oh. Damn it. I already showed everything. FM. What other?
Would it be FK1?
No, FK1 is already here.
Okay.
It is going to be FK2. Core thing. Never ever forget that one. Many other things hang around the balance. The spring is 99.9% between 2 nodes. Okay, so that one is directly connected over here too. So FK2. So let's write the equation. So F B1 plus F K1 is equal to FM plus F K2. Third node. This particular one. Tell me how many forces are acting on this particular node.
2.
2. What is on this side?
FK2.
FB2.
F K2. And on this one is FB2.
B2.
These are the body diagrams. Okay, we are not out of the woods yet. Okay, now, so we want to write these 3 equations. 1, 2, and 3. The third one is F K2 is equal to F B2. That's it. So these are the 3 equations. I want you to remember these 3 equations. free body diagram on a specific node is 100% identical to the voltage equations on a loop. Do we understand that one, sir?
Yes.
Yeah.
So when we write the voltage equations, I would say V external is equal to V. What was a B corresponding to? The friction was corresponding to the resistance, VR1. What was K corresponding to? The spring constant.
Conductor.
1
Is
over
it
C.
capacitance?
1 over C.
Capacitance, VR1. I'm just going to
Yeah.
write the equation for now.
Gotcha.
Okay. The second equation for this one,
Would it be VC1?
that would be correct. Okay. What about this one?
VL plus VC2.
What about the third one?
VR2.
VC2.
VR2?
Okay. So far, so good. There is one small element that we have to be careful about. And that element is crucial. You need to realize that there is an interconnection. You see this VR1 and VC1, they are in the second loop also. Do you see this one?
Mm-hmm.
Okay, before I go that one, let's talk about F. Okay, so this frictional component
Node 1 and 2.
node 1 and 2. So actual representation is V1 minus V2. And the other one is A1 X1 minus X2. This is actual true. Okay. Yeah. All right. Did I confuse you enough or no? Because this is between the nodes and they are identical over here. Like this one. Okay. So what about equivalence over here? What is a VR1 now? Does it make sense or no? Please tell me.
Yes, kind of.
But when we talk about the analogy wise, we just put this one. And this is identical. What about this one? VL. Okay. So when we talk FM, can you see that M is directly connected to how many nodes it is connected to?
2.
This is M is only connected to 1. This is not connected over here. This one is M is not connected to the second node because only the M is only connected to this particular one, the node 2. It is not connected to node number 3. So this one is the FM is nothing more than M A 2. basically, or we could put M X double dot 2. That's all. However, FK2 is connected to this one. When we talk about the FK2, it is the spring constant, unless, and you will see some cases that it is like this one. Then there is only one node over here, but this is not the case. I'm just gonna delete it because that's it. So FK2 is between the two nodes plus K2, and this was a X2 and X3. And this one would correspond, this is the exact same one. So VL would be equal to L I2 plus C2. What are the currents? This is the key. What would these currents be? Did I lose everybody?
Still here, Professor?
Huh? I'm waiting for your acknowledgement, yes or no.
Yeah, we're still here.
Yes, sir.
But do you understand it? That's the key.
Mostly yes.
You
Okay.
lost me.
I'm going to do another example, you get it.
Yeah.
So this is VC2.
Okay, thank you.
Thing. So it would be CE, C2, I2 minus I3. This one is only related to like this one. So this was like a BV3, and this one was equal to the K2 X2 minus X3. All of this one, by the way, is given right here. So remember I was talking about the free body diagram equations. Did I not?
Yeah.
The free body diagram? The free body diagram in mechanical system is equal to
KVL.
voltage equations of loop, which are called the KVL, and you are correct, KVL equation. So free body diagram in mechanical system is identical to the voltage equations of KVL. That's what it is. So we had this one, remember? I put F ext was equal to FB1 plus FK1. That was the one. This one was FB1 plus FK1 was equal to FM plus FK2, and FK2 was equal to B2. So these were the three equations. So this is, and then each one, when we talk about the FB1, is basically this one, and corresponding electrical is this one. FK1 is this one. It should actually be X1, okay? Not that one. Okay, and this is the one. So similarly, and this should be X2. Okay, because really when it is a K, it is the displacement and not the velocity. That's why we put it over here. Okay, so this is the voltage equations of the loop are identical to the free body diagram equations in the mechanical system. One last step left. Somebody tell me what it is. The actual electrical circuit. So let's write it. So the Vn, I have the voltage in, and there are two forces which are